we discussed the Cauchy sequence. So Cauchy sequence means that a sequence is said to be Cauchy sequence if for every epsilon positive there exists a positive integer n such that d xm xn is less than epsilon. That is to say, if you have after each mn, so you have a capital N, a natural number. So after this, okay, so the elements of the xm, xn, so the distance between these two sets is less than epsilon. So this is the length, so all lies in this one. Okay, so after this, the elements are is less than epsilon. So this you can say Cauchy sequence, and then we have seen several examples of a Cauchy sequence, and we have already proved that every convergent sequence is a Cauchy sequence, and then we proved that, but the converse is not true. Every Cauchy sequence may not be. We have several examples. Every Cauchy sequence may not be convergent, but if every Cauchy sequence is convergent in a metric space X, then X is said to be complete. And we have seen several examples of a complete metric space. So here we have seen several examples of a complete metric space. Okay, several non-complete metric space, and there here we have seen that with respect to max sup matrix or D infinity matrix, CAB is complete, but with respect to the integral metric, with respect to this metric, CAB is not complete. And not only this, you can define many other matrices, and you can see that set of all rational numbers is also not a complete metric space. Okay. So there are several examples, exercises, and we have seen several other results. And then another important result that is called the Cantor intersection theorem. So Cantor intersection theorem says that let XD be a complete metric space. XD be a complete metric space and Fn be a decreasing sequence. Okay, decreasing sequence means Fn plus 1 is a subset of Fn. So Fn is a decreasing sequence of non-empty closed subset of X such that the diameter of Fn converges to 0. Okay, then the intersection of all these sets contains exactly one point. Okay, so this means it is something like this. Suppose you have a decreasing sequence. This is your F1. So F1 contains F2. This is your F2, and then F3, then so on and go, and in such a way that the diameter of Fn. So this is your here you have the diameter of this, the diameter of Fn converges to 0. Then the intersection of all Fn contains exactly one point. So that is the Cantor intersection theorem. Okay. And we prove that in the Cantor intersection theorem, these two conditions are necessary. Okay. If we drop any of them, then the result may not hold. And we have seen that the converse, okay, of the theorem in this case, that if X is a metric space and every decreasing sequence Fn or non-empty closed sets whose diameter such that the diameter of Fn converges to 0 has exactly one point in the intersection, then the space is complete. Okay, so this and then several exercises, and the completion, we have proved that completion is what? Completion means a set is complete if every Cauchy sequence is convergent. So you have a Cauchy sequence, it may not convergent. So it will be convergent if you collect all the limit points of all the sequences. Okay, so suppose you have a set X which is not complete, then you can include in this set a larger set or the elements limit points of all the sequences, and it will make you a complete metric space. So in a complete metric space, X star D star of the metric XD is said to be completion of X if X is a subspace of X star and every point of X star is the limit point of subsequence in X. And then we have seen several examples of the completion of a space. Okay, and we have the proof that every metric space has a completion. So here is every metric space has a completion, and this we proved. Okay, so that way we have completed 2 chapters. And then the third one chapter is regarding to the third chapter. Okay, so I take a pause over here, and then we can start the next talk. But we will continue in the same way. Okay, so here is we see that the countable we defined the base. Base means that if you have O is a family of open subsets of X, then a subfamily of open subsets of X is called a base for O if every open set in O, every open set G in O is the union of members of B. Okay. Further, if this family B is countable, then we say that it is a countable base set. But this, okay, can be characterized in the following way, that if O is the family of open subsets of X, then the subfamily of the family OB, okay, is called base of O for O if and only if every point X belonging to an open set G, there exists an element in B, there exists an element Bx in B such that X lies in Bx and B is a subset of X. So by using this characterization, we can check whether a subfamily of open set is a base or not, or a countable base or not. And this we have studied well, and then several examples we have studied, and then we have mentioned that a metric space X is second countable, okay, or second axiom space if there exists a countable base for the family of open sets. If there exists a countable family of open sets, then X is called a second countable space or second axiom space. We provided several examples, okay, and then of course, because you see it is really very strange. First we are defining the second countable space, and then we are talking about the first countable space. So because there is no direct relation between the first countable and second countable. So first countable means a metric space X is said to be first countable space or first axiom if for every point X there exists a countable family B and X of open sets containing X such that every open set G containing X also contains a member of B and X. Okay, that was the definition of the model. Every second countable metric space is first countable, but the converse is not true. So this we have provided, and we have also proved that every metric space is a first countable space. So every metric space is a first countable space. Then we defined the dense set. Dense set means a subset of a metric space X is said to be dense if the closure of this set is equal to whole space. So the set A is a subset of X, it is called dense if the closure of A is equal to X. Okay, and then we mentioned this is very important characterization. So A is dense if and only if the distance from the point X to A is equal to 0. If and only if A has non-empty intersection with every non-empty open subset of X. So this we proved. Okay, then we provided several examples of dense set. Okay, here several examples we provided that, and we proved that if Gn is a sequence of dense open sets in a complete metric space, then the intersection is also dense. This we proved. And then we defined the separable metric space. So a metric space X is said to be separable if there exists a countable dense set. If there exists a countable dense set, then the space is called separable spaces. Then we defined several examples of a separable spaces. So here are several examples we discussed, and then a metric space X is separable if and only if it is a second countable. So here you have a metric space is separable if and only if it is second countable. So basically the second countability used to prove that the space is separable. Okay, then several examples, and other ways we have a nowhere dense set. So a metric is a subset A of a metric space X is said to be nowhere dense set in X if the interior of closure of A is equal to empty. That is to say, if the closure of A contains no interior point. Okay, and there is no direct relation between the dense set and nowhere dense set. We cannot say that if the set A is not dense, then it is nowhere dense set, or a set is not nowhere dense set, then it is a dense set. We have provided you several examples. Okay, but you can say that if a set A is nowhere dense set, then the complement of closure of A is dense. So a set A is nowhere dense if and only if the complement of the closure of A is dense. But in direct you cannot say this thing. Okay. Then we mentioned about the second category. Second category means you have a subset, first category or second category. A subset A of a metric space X is said to be of first category if it is countable union of nowhere dense set. So a subset of a metric space X is said to be of first category if it is a countable union of nowhere dense set. Okay. Otherwise, it is called of second category. Okay. Then we provided several examples, and we proved that the bare category theorem, which is very important, and we say that every complete metric space is of second category. Okay. So here we have every complete metric space is of second category. Then several examples. Okay. And then we have the compact metric space. So compact metric space, we seen that in the reanalysis, in case of reanalysis, we say that a closed and bounded subset of R is compact. So the definition of the compact set was in reanalysis that a closed and bounded subset of R is compact. Okay, or a set is, we say that is a compact, it means that it is closed and bounded. But it is not true in general in the setting of metric spaces. We cannot say that a closed and bounded subset of a metric space is compact. We will have to give the proper definition in the setting of metric space. So first we define the cover. Okay, so cover a collection F of subsets G alpha subsets of X is called a cover of X if the union of G alpha is equal to whole X. If the union of G alpha is equal to whole X. That is to say, if you take for every point in capital X, there exists G alpha contains that point. Okay, and if the members of this collection are open sets, then this collection is called an open cover of X. And a subcollection F, subcollection C of F is called a subcover of F if this subcollection itself a cover of X. That is to say, if there exists G alpha 1, G alpha 2, G alpha n. Okay, so this is called subcollection of F. If this subcollection is finite, okay, then it is called finite subcover. Okay, so F is called finite subcover if it consists only a finite number of members. In the other words, if there exists G alpha 1, G alpha 2, G alpha n in F such that the union of G alpha i's is equal to the whole space X, then this subcollection is called a finite subcover of X. And then we define with this, we can define the concept of compactness in a metric space. So, a metric space X is said to be compact if every let us define the cover of a subset or subspace. So, let us take X metric space, Y is a subset of X, then the collection G alpha of subsets of X. Keep in mind, this is a collection of subsets of X is said to be cover of Y if the union of this contains Y. Union of this contains Y. And then we define, so here is the example of collections open cover, and then we can define the compactness. So, compactness in a metric space X is said to be compact if every open cover of X, this is very important, if every open cover of X has a finite subcover. Every open cover of X has a finite subcover. Okay, now you see that it is very difficult to check because there are maybe many open covers of a set, and it is difficult to check whether every open cover of a set has a finite subcover. So, we will have some characterization. So, a subspace Y dy of a metric space XD is called compact if it is compact as a metric space in its own right. Okay, and then we provided several examples. Okay, several examples of a compact set, and we have mentioned that here it was very important example that Y is compact if and only if every cover of Y by sets open in X contains a finite subcover of Y. So, there is by using this we can see that whether it is open in X or open in Y, it is okay, no problem at all. And then we prove that the closed subset of a compact metric space is compact. Okay, this we proved. Every closed subset of a compact metric space is compact, and then we have mentioned that arbitrary any intersection of compact set is compact and finite union of compact set is compact. And then we provided a definition which is called finite intersection property. So, a collection of subsets of a metric space X, C1, C2, Cn, this collection of a metric space X is said to have the finite intersection property if every finite subcollection of this collection has non-empty intersection. For example, if we are getting C1 intersection C2 must be non-empty. If we are considering C2, C3, C4, C5, C7 intersection, then it is non-empty. If we consider C2, C4, C6, C8, the intersection is non-empty. Okay, so any collection, any finite intersection of elements of this set has non-empty intersection, then we say that this family has finite intersection property. And we have seen several examples of finite intersection property, and then we prove that as a characterization of a compact space, that a metric space X is compact if and only if every collection of closed sets in X having finite intersection property has non-empty intersection. Okay. So a metric space X is compact if and only if every collection of closed sets in X having finite intersection property has non-empty intersection. So this we have proved, and then we also proved the converse of this. We proved, so here are several examples we proved, and then we defined the sequentially compact metric space. So before that we defined the Bolzano-Weierstrass theorem. Bolzano-Weierstrass theorem says that if A is a closed and bounded subset of R, then every infinite subset of A has a limit point in A. That was the Bolzano-Weierstrass property. Now, we generalize this Bolzano-Weierstrass property for the metric spaces. So, a metric space X is said to have the Bolzano-Weierstrass property if every infinite subset of X has a limit point. Every infinite subset of X has a limit point. And then we prove that every compact metric space has the Bolzano-Weierstrass property. And then we defined the concept of sequentially compact. So a metric space X is sequentially compact if every sequence in X has a convergent subsequence. So every sequence in X has a convergent subsequence. And then we prove that a metric space X is sequentially compact if and only if it has the Bolzano-Weierstrass property. And not only this, we prove that in particular every compact metric space is sequentially compact. And then we prove we prove that every closed subset of a metric space is every compact subset of a metric space is closed and bounded. Okay, every compact subset of a metric space X is closed and bounded. But keep in mind, a closed and bounded subset of a metric space need not be closed, need not be compact. So, and then we define basically the main goal of this chapter was to study the compactness, and then we defined the compactness, Bolzano-Weierstrass property, and sequentially compactness. And we proved that all these three concepts are equivalent. So to prove that they are equivalent, we defined the totally boundedness of the space. So before that, we defined the epsilon net. So a subset A of a metric space X is called an epsilon net if A is finite, and if we take for each point, because it is a finite set, so for each point we have an open sphere with radius epsilon, and take the union of such open sphere that should be equal to the whole space. Okay, then A is called an epsilon net. And then we defined, so here the several examples, and then we defined the totally boundedness. So a metric space X is said to be totally bounded if it has an epsilon net for each epsilon is greater than 0. So for each epsilon it is greater than 0, it is called an epsilon net. And then we prove that every sequentially compact metric space is totally bounded and complete. So keep in mind, at last we will prove that the sequentially compact metric space, Bolzano-Weierstrass property, they are all equivalent. So in other words, you can say that every compact metric space is totally bounded and complete. Right, not now, but later we can say, because when we will prove that all three concepts are equivalent. So we will prove, but so far we have every sequentially compact metric space is totally bounded and complete. Then, but every totally bounded metric space, okay, totally bounded metric space need not be sequentially compact. Every complete metric space need not be compact or need not be sequentially compact. But every totally bounded complete metric space is sequentially compact, because the totally bounded plus complete, then you have a sequentially compact. Okay, so this we proved, and we proved that every totally bounded metric space is separable, and then we defined the Lebesgue number. So if you have an open cover, okay, open cover of X, then lambda greater than 0, it is called Lebesgue number. For this open cover, if for each subset of X whose diameter is less than lambda is contained in at least one G alpha, okay, then it is called an open cover. And then we mentioned Lebesgue covering lemma, which says that every sequentially compact metric space in a sequentially compact metric space, every open cover has a Lebesgue number, and by using the Lebesgue number, we prove that every sequentially compact metric space is compact, and we have already proved that the every compact set is sequentially compact, and therefore both are equivalent. So finally, what we did, we proved that the compactness, so sequentially compactness implies compactness by using this theorem, and compactness implies Bolzano-Weierstrass property, and Bolzano's property and sequentially compactness are equivalent, and therefore all these three concepts are equivalent. This we have proved, and then we discussed several results. Okay, so now I stop, and we will continue revising the last two chapters.